to find a percentile. Remember, the percentile is the amount of the population before that value, which translates perfectly to our understanding of the area under the curve, which if I have the z-score, then our cumulative normal distribution chart can help us. So let's bring up the chart. Here we have the chart, and we're going to try to identify what z-score gives me an area closest to 0.85. Now here we're going to just have to look through a lot of these values and try to find the closest and kind of zoom in farther and farther. So I can see around the 0.9 to 1.2, I'm in the 0.8s. So specifically I want to be at 0.85, so I'm going to highlight a few that are close. 0.8485 is close. 0.8508 is close. I look and I don't see any closer contenders. So remember, how do you determine between two things? You figure out which is closest to 0.85. So which of these two seems closer to 0.85 to you? Well, the 0.8485 is 0.0015 away, whereas the 0.8508 is only 0.0008 away. So that's why we'll use this value. Now this value corresponds to the row of 1.0 and the column of 1.04, so to get a probability of 0.85, that corresponds to a z-score of 1.04. Let's write that on our notes. So here we're looking for a z-score of 1.04. So if you have a z-score of 1.04, you have a value that is greater than 85% of the population. Now the z-score here is not enough. We want to then translate this z-score location back away from standard normal, back into our normal population that had this mu and this standard deviation. Now keep in mind, what translates z-score back to the normal population is the z-score formula of the z-score is the data value minus the mean divided by the standard deviation sigma. Now here we have a lot of these values. We know the z-score in particular is 1.04. We don't know the data value that corresponds to this z-score, but that's what we're looking for. It's okay if there's one unknown. Minus the mean of 56 divided by the standard deviation of 8. And now I have an equation that I can solve. Some x value, if you subtract 56 from it and you divide it by 8, will give you this z-score. Why is this z-score important? Because this z-score is the cutoff that has 85% of the population below it. So if we can just find this value of x, we'll have solved the problem. Now how do we find the value of x? It's using algebra. We want to get x by itself. And how would you do this? If you had x, you would subtract 56 first and then divide by 8. So whenever you solve, you reverse that process. To get x by itself, I now want to multiply both sides by 8. Cancels from here, and we would get, let's see in our calculator, 8 times 1.04, and we get 8.32 is equal to x minus 56. To get x by itself, we'll add 56 to both sides, and we get the x value that we were looking for is 64.32. So this x value will correspond to being greater than 85% of the rest of the population. According to a recent report, the weight of male babies less than 2 months old in the United States is normally distributed, and we have a mean of 11.5 and a standard deviation of 2.7 pounds. We're asked to find the proportion of babies that weigh more than 13 pounds. So we have a normal distribution. We know we can only find proportions, probabilities, areas under the curve in the standard normal. So our first step is to turn this 13 into the corresponding z-score, which will give us the standard normal location in the curve. Okay, so 13 minus 11.5, our mean gives us 1.5. Divide that by 2.7, and we're going to get ready to round to 2 decimal places. and that's about 0.5. After the 5 is another 5, so we round up 0.56 for our z-score. Now I need to keep in mind, whenever you look at this in the cumulative normal distribution chart, the area you're going to get is area to the left. But since they want us to find the value that weighs more than 13, the chart does not give us that directly. So instead, we need to find the proportion that is less than our z-score of 0.56 from the chart, which is equivalent to the x value of 13, and then take that value and subtract it from 1. That's how we're going to get the more than. So let's bring up the chart and find 0.56 as our z-score. Okay, so here we're looking for 0.56. We've got our 0.5 row, our 0.6 column. That gives us an area before of 0.7123. Okay. So that's the amount less than. We want to find the amount more than, so we take 1 minus the amount less than. And here I realize I wrote these out of order. It's 0.7123, so let's correct that, and then we'll write that as we subtract. When we subtract that from 1, we get the value 0.2877. So as you work through these problems, pay special attention to the context clues. Are they looking for less than? If so, that's directly using the chart. Are they looking for more than? If so, you need to find the chart value and subtract that from 1. Or if it's between, remember it's the chart value for the larger minus the chart value for the smaller. And the concept behind those calculations was covered in greater detail in the last video where we first started working with z-scores and the chart. This video just adds the extra step of actually calculating the z-score before we use the chart. So in our next question, we have what proportion of babies weigh less than 15 pounds? Less than is a direct use of the chart. So I know all I have to do here is turn the 15 pounds into a z-score, then reference the chart to find the amount of area enclosed before that z-score, which is equivalent to the probability that if I randomly select a baby, it would be less than 15 pounds, which is equivalent to the proportion of all babies that weigh less than 15 pounds here. So setting up to find the z-score, we get 15 minus the mean divided by the standard deviation. Now 15 minus 11.5 will give us 3.5. Divide that by the standard deviation, and we know we'll round the result to 2 decimal places. So we get 1.296. Now as we round, we know we want to round to the second decimal place. So we go 1 over, and that's a 6. Since that's greater, we round up. So we round the 9 up. But when you round the 9 up, that's really rounding 29 up. So we round that up to 30. So that gives us a z-score of 1.3. Let's look at our chart and see for a z-score of 1.3 what the area is under the curve, which is equivalent to the proportion. And since it's less than, we know once we get that answer, we'll be done with this problem. So looking at the chart here, I find the row for 1.3. I find the column for 0.00, so that'll give me 1.30. And the area or proportion of results before that value is 0.9032. So our answer here is 0.9032. Now for the same setup, we're asked the next question, what proportion of the babies weigh between 10 and 14 pounds? We know from our previous lesson, the between problems is I need to calculate the amount for the larger, so the area before 14. I need to calculate the area before 10 and then subtract them. Now, before I do that, I can't really find the area before 14 because that's a normal value and I need a standard normal value. So I'm first going to turn this 14 into a z-score. My z-score will come from 14 minus 11.5, the mean, divided by the standard deviation of 2.7, and that will be a z-score of 0.93 when rounded. And similarly, let's find the z-score for 10. The z-score is 10 minus the mean and we'll get a z-score of negative 0.56 when rounded. So now that these are turned into z-scores, I can find the area before the larger z-score and subtract it from the area before the smaller z-score. Now for 0.93, let's look and find that in the chart. Here's my row for 0.9. Let's cross that with the 0.003. So the amount of area enclosed before the 0.93 is 82.83. We'll write that down. Excuse me, 0.8238. I misspoke earlier. Next, we'll find the area for the z-score of negative 0.56. So here we find our row for negative 0.5. Cross that with the column for 0.006 or 0.06. And we get an area that corresponds to 0.2877. Now we know the 0.8238 is an overestimate because it has everything below the z-score that corresponds to 14. We only wanted the values between 10 and 14, so we correct that overcounting by subtracting the portion that lies below 10, following the structure from a previous lesson. And we get the total area enclosed between the values 10 and 14, which is equivalent to the proportion of babies that weigh between 10 and 14 pounds is 0.5361. Now our final question is it unusual for a baby to weigh more than 17 pounds? Now our cutoff for if it's unusual would be if the probability of more than 17 pounds is specifically less than 0.05. If the probability is less than 0.05, then we would say yes, it's unusual. If the probability is instead greater than 0.05, we would say no, it's not unusual. So that's our cutoff for what we call unusual in this class. Now, to find the probability of more than 17, I first need to turn 17 into a z-score. From the z-score, I can get the chart of the probability of less than that value. Then to turn that into a more than, I just take 1 minus that. So that's kind of going to outline what we're going to do here. Let's first find the z-score that corresponds to 17. Remember, our mean is 11.5. Our standard deviation is 2.7. So we get a z-score of 2.037. When we round that, that becomes 2.04. Let's find the probability that we would be less than that value. That's what we get directly from the chart. And then we can translate that into more than the value. So looking at the chart for a z-score of 2.04, the area before that to the left or less than that is 0.9793. So that's our probability less than. We actually cared about more than. So we take 1 minus the less than number. And the likelihood that a baby would weigh more than 17 pounds is then found to be 0.0207. That is specifically less than the unusual cutoff of 0.05. So we would say, yes, it would be unusual if a baby at 2 months weighed more than 17 pounds. Now in our example here, we've got the weights of commercially raised chickens are approximately normally distributed. We've got a mean of 1387 grams and a standard deviation of 161 grams. For part A, we're asked to find the 22nd percentile of weights. Now we've dealt with percentiles before. The percentile is saying what value is greater than 22% of the population. Said another way, what value has 22% of the population less than it? So we're interested in the z-score that has 0.22 of the area under the curve less than that value. Now, in order to do that, we need to go to the chart, and we're doing kind of the reverse process. We've given the area, and we need to find then the z-score. So for an area of 0.22, I know I'm in the negative region because at exactly 0 I'm 0.5, so 0.22 should be somewhat negative. So we go to the negative portion of the z-score chart and we look for values close to 0.22, and we're just going to have to go through a few and we'll find some of the closest and then we'll determine which ones between those two. So I see a 0.2206, I see a 0.2236. I don't believe I see anything closer than those two. So between those two contenders, which one's actually closer? Well, the 2206 is closer. So that's our area of 0.22, as close as we can get. So then that corresponds to a row of negative 0.7. And let's see what column that is as well. I'll have to zoom out. It's a column of 0.07, so my z-score that corresponds to this area of 0.22 is negative 0.77. So we know the z-score, but we want to then translate that back. This is a standard normal value. We want to translate that back to the normal distribution. So to do that, we solve our equation of z-score. Z-score is the value minus the mean over the standard deviation. So for us, that will be, so we get our z-score of negative 0.77 is equal to our unknown x value that corresponds to that minus the mean of 1387 divided by the standard deviation of 161. We'll solve for x by multiplying both sides by 161. And we get that value. Now to get x by itself, we need to add 1387 to both sides. We're just going through the algebra in our calculator. And we get an x value of 1263.03. And if you want to kind of check why this works out, start with this data value and reverse it. Find the z-score, see that you will get negative 0.77. Then from that z-score, see that the area under the curve before that is 0.22, which corresponds to the 22nd percentile. Now for the next problem, it says find the first quartile of weights. Here we need to translate that verbal description. Quartile is quarter, so the first quarter corresponds to the 25th percentile. Once we've translated that phrase, this question is much like what we did in part A. Because of that, I encourage you to pause the video and attempt it on your own, then unpause to check your work. So let's look at the chart to find the z-score that corresponds to 0.25 of the area under the curve less than it being there. Looking at the chart, it looks like the closest contenders are 0.2514, 0.2483. Now the 0.2483 is 0.0017 away, the 0.2514 is 0.0014 away, the 0.14 is closer, so this is our value we're going to go with. Let's find that z-score by looking at the row and column it came from. So it came from the negative 0.6 row, the 0.07 column, so that z-score is negative 0.67. Once we have the z-score, we can set up the formula to isolate and find the corresponding x value that would give us that z-score, given our mean and standard deviation. And we can solve this step by step using algebra, and we can also solve it using our calculator. So we can kind of go through the steps either by hand or in the calculator. We know the first step of solving would be to multiply both sides by 161, so we do that in our calculator, and we get this value. Then the next step to isolate would be to add 1387 to both sides. So we get the isolated x value is 1279.13. And that x value, given the mean and standard deviation, would put you in the 25th percentile of weights. Now our last question here, what is the probability that a randomly selected chicken weighs more than 1,500? Now we've done problems similar to this in this video before, so I would encourage you to now pause the video and attempt this problem on your own, unpause to check your work. Use this as an opportunity to gauge how well you're understanding the material to this point. We know when we're asked about more than problems, that's going to be kind of a indirect approach using the table. We need to find the probability of less than 1,500 directly from the table, and then to get more than, we'll subtract that value from 1. Now before I can even go to the table, I need to turn this 1500 into a z-score. So I've got the data value of 1500 minus the mean of 1387 divided by the standard deviation of 161, and remember we'll round that to 2 decimal places. And we get a value of 0.70 as my z-score. Let's find the area into the chart. Keep in mind that once we find the area, that's not our final answer. That is the amount less than. To find the amount more, we say 1 minus that. So for a z-score of 0.70, I'll find the row for 0.7, cross it with the column for 0.00, and we get an area encompassed before 0.7 is 0.7580. To translate that into what we're looking for, to find the probability of more than, that will then be 1 minus 0.7580, which gives us 0.2420.